See, there are two technical terms related to this. One is covalency, as I have written here. So, what is the meaning of covalency? Covalency is a very important point. So, the covalency is the number of covalent bonds to an atom, right? So, covalency is related to the number of covalent bonds to an atom, right? And what is coordination number? Coordination number. See, coordination number is the number of atoms bound to another atom, right? So in most of the cases, covalency is same as coordination number, but not in all cases. So in most of the cases, most of the cases covalency is same as coordination number, but not in all cases. Right? Not in all cases. Now see, with an example, I will explain what is covalency and what is coordination numbers. For example, see, suppose that we have PF5, right? So if you see PF5, so this is the structure of PF5, and if you see here, so what is the covalency of phosphorus here? Define number of covalent bonds. So how many covalent bonds are there? 5. So the covalency is 5, right? How many sigma bonds are there? All are sigma. 5 sigma. Number of pi bonds? 0, right? Okay. What is the coordination number? Number of atoms bound to another atom. So suppose that phosphorus, we are talking about the phosphorus. So phosphorus is bounded with how many another atom? 5. 1, 2, 3, 4, 5. So here coordination number of phosphorus, this is equal to what? 5. And what is the coordination number of fluorine here? So coordination number of fluorine here is 1, right? See, number of atoms bound to another atom. So this 5 atoms are bonded with the phosphorus, so the coordination number of phosphorus is 5, and coordination number of fluorine. This is bonded with only one phosphorus, so this is 1. And here covalency of phosphorus is 5. And if it is asked covalency of fluorine here, so this is 1. Covalency of fluorine, so this is equal to 1. Right? Clear? See. And how many electrons are there in the valence shell of phosphorus? So the number of electrons in the valence shell of phosphorus is equal to number of bonds 5. So 5 bond pair, and 5 into 2 is equal to 10, right? 10 electrons. So if someone is asked, okay, tell how many orbitals of phosphorus are used here, right? So how many orbitals of phosphorus are used here, in this molecule, So total 10 electrons. 10 electrons means how many orbitals? 5 orbitals. So 10 by 2 is equal to 5 orbitals, because one orbital can have 2 electrons, right? So in this molecule, so the answer is number of orbitals is equal to the number of electrons by 2. So this is equal to 10 by 2 is equal to 5, and this you can also write the number of bond pairs. Number of bond pairs is equal to the number of orbitals, always. This is always true. So here 5 orbitals of this phosphorus are involved. So if it is asked, okay, tell this molecule is obeying octet rule or not, so you can say, okay, there is no obeying here octet rule, because there are 10 electrons in the valence shell. So this is called superoctet. Means it is violating octet rule, and it has more than 8 electrons in the valence shell, right? And it has this molecule has more than 8 electrons in the valence shell, means this is violating octet rule. Superoctet, you can say, superoctet. 10 electrons means superoctet. Okay, hopefully all of you are clear in this regard, that what is coordination number, what is covalency, and how many orbitals are involved, how many sigma, how pi bonds are there in the molecule, right? So hopefully it is clear. And now see, I have not shown here, but you know the number of lone pairs, 3 lone pairs are there in the fluorine. If you examine fluorine here, so fluorine also have how many electrons in the valence shell of fluorine? 8. See, because fluorine cannot violate the octet rule, because this belongs to the second period, so this cannot have more than 8 electrons in the valence shell. So in the fluorine, if you examine fluorine, so number of bond pairs plus number of lone pairs is equal to 4, right? And 4 orbitals are definitely involved here in case of fluorine. Now let's see what 5 different orbitals of phosphorus are involved here in this molecule. So again you have to go in the this electronic configuration. So 1s2, 2s2, 2p6, 3s2, 3p3, right? Now see, okay, from here to here this is core. This is core. And this is valence. And you know this 3D 0, it is present but no electrons are there, so this orbital is called virtual. So any atom can have 3 set of orbitals. Core orbitals, they do not participate in the bonding. Valence orbitals and virtual orbitals. So valence orbitals means valence shell orbitals have some electrons, less are complete. That is a different issue. But if there are some electrons, then you should count that in the valence orbital. And valence shell orbital without electron, that is called virtual orbital. That is called virtual orbital. So in bonding, not only valence orbital, virtual orbitals may also involve. But core orbital, no, not at all. In any kind of bonding, core electrons will not involve. Here in valence bond theory or in the hybridization, whatsoever. Okay, in molecular orbital theory we are using this. But in the normal here in valence bond theory, we are not advocating to participation of core orbitals in the bonding. So here valence orbitals and virtual orbitals, they can participate in the bonding. We are talking about this molecule PF5. We have started discussion for this molecule PF5. Now come to the Hund's rule. That's why I told you atomic structure is very important to understand further, and further for the understanding of further chemistry, this is very important. So slowly we will do everything. See 3s, Hund's rule you have to apply. This 3p3, okay, 3p3. Now this is the electronic configuration. Now tell me, is it possible that, and see 3D is virtual and no, okay. So this is the, electronic configuration of phosphorus atom, ground state electronic configuration. So can this electronic configuration can explain this formation of this PF5 molecule? The answer is no. How? See here, number of orbitals, 5 orbitals, from where you can accommodate, find. See, can this orbital overlap with fluorine? The answer is no. Why? It cannot, because it has already 2 electrons. So how it can overlap? See, only these 3 can overlap with 3 fluorine, but this orbital cannot overlap because it has already 2 electrons. Clear? Clear or not? This orbital cannot involve in the bonding. So 3s electron in phosphorus cannot involve in the bonding, because it is already fulfilled. 3p, x, y and z, they can participate, but only 3 bonds it can form. So what will happen? It means the electronic configuration of phosphorus, this electronic configuration of phosphorus will not exist in this PF5 molecule. So what conclusion we can say? That 3s orbital cannot participate in bonding thus no orbitals are available because sharing is there, bonding, thus this electronic configuration is not uh, existent, exist in PF5. Then what will happen? Then the concept of this excitation will come. So how this excitation, this is the core of neon. Now I am writing this as a neon, and then this 3s1, 3p3 and 3d1, right? Now see, 3s, now 1 electron, 3p, now see, you can see there are 3 electrons, and now this 3d, this has 1 electron. Now you can see that 1 fluorine can make a bond with this, 1 fluorine can make bond with this, 1 fluorine can make bond with this, 1 fluorine can make bond with this, and 1 fluorine can make. Now you have 5 orbitals. So these orbitals okay, these orbitals are involved in this formation of PF5 molecule. So this is the maximum covalency of phosphorus. Now, can phosphorus expand this octet beyond this? The answer is no, because you know in covalent bonding, one electron, both the atoms should participate. So in the orbital, if one electrons are there, now more than this it cannot expand. So this is the maximum covalency of phosphorus, and the maximum covalency of phosphorus is 5. Core electrons cannot be promoted to the valence shell, because core electrons are not participate in the bonding. Okay, so this is the maximum covalency. So what I have written here, see, maximum covalency of group 15 is 5, right? And normal other covalencies is 3. So when group 15 element, not all except nitrogen, if they are here in covalency 3, then they obey the octet rule, and when they are in the 5, then they disobey the octet rule, right? So this is the complete explanation of one of this kind of molecule. Now you can do the same thing, explanation for this. This is homework for you people. I am writing this structure, I am writing, and all of you should explain How see here now one more thing you can see here, in this state it has covalency 3. Here the covalency is 3. Covalency is 3 here, and here the covalency is 5. Here the covalency is 5. So in this state the covalency is 5. This is the excited state. Excited state, and here the covalency is 5, and coordination number I have already written all these things. Coordination number is also 5. So now I am writing some structures, and all of you should write coordination number, covalency, and different electronic configuration of the elements. SF6, this is also a superoctet, right? This is the SF6. So all of you should do the electronic configuration of sulfur, how many electrons are in the valence shell of sulfur, and it is not obeying the octet rule, right? Similarly, IF7. IF7, right? IF7. Similarly, XeO4. See here, XeO4 here. If you see here, what is the covalency of this? Covalency, maximum covalency, number of bonds. So you have to count this 2 bond, 2 to 4 to 6 to 8. So the covalency is 8. What is the coordination number of xenon here? What is the coordination number of xenon? How many atoms are linked? 4. So see here, the covalency is 8. Number of covalent bonds 8, but the coordination number is 4. Clear? So here covalency and coordination number are not same, right? So this is XeO4. So all of you do all these things, write the electronic configuration, right? See here how many electrons in the valence shell? 6 to the 12. So there are 12 electrons here. 7 to the 14. Here 14 electrons, and here how many covalency? 8 to the 16 electrons, right? So 16 electrons, 14 electrons, and 12 electrons. So these are the maximum, these are the number of electrons in the valence shell, right? One more point is left for this fourth point, and this is, I think, in my opinion, this is the most important point. What is this? It has been assumed, assumed implicitly in all of these rules, that the molecule will will seek the lowest lowest overall energy. Overall energy. See whether molecule obeying octet rule, not obeying octet rule, that is not the criteria for existence of any molecule. The criteria is energy. If its energy is in the lowest, total energy means repulsion and attraction or resultant. If resultant is in the total energy, resultant of total energy for any molecule, it is, if it is overall lowest, the molecule will exist and everything is fine. But if any molecule obeying octet rule and have much larger energy than the constituent atoms, the molecule will not exist. So ultimately the main criteria for existence of any molecule, that is what? Basically energy, right? Now see how we sketch the Lewis model for any molecule or ion whatsoever it is given. So first point of this is decide calculate the total number of, first point is calculate the total number of valence electrons in all the atoms present in molecule oblique ion, right? And see one more thing here, that if there is positive charge, then less the number of electrons equal to the number of positive charge, and if there is negative charge, then add the number of electrons. So some sub cases are there. If positive charge is there, then remove the electrons equal to the number of positive charge, right? Second part, if negative charge is there, then add the electrons is equal to the number of negative charge, right? For example, see, suppose that H2O is given. So this total number of electrons total number of electrons is equal to valence electrons basically. So there are 6 valence electrons in oxygen and 1 in hydrogen. So 6 plus 2 is equal to 8. Suppose that NH4 plus is given. So total number of valence electrons basically, valence electrons. So total valence electrons is equal to 5 in case of nitrogen, 5 plus 1 in case of hydrogen. So 4 into 1, 4, and 1 positive charge is there, so minus 1. So you have total 8 electrons, right? Similarly, if you have PO4 3 minus, so the why I am writing total valence electrons, it is total electrons, not valence electron, right? No, sorry, total number of valence electrons basically in all atoms that I have. I mean total number of valence electrons, right? Okay, valence electron is okay in the whole molecule. I have, I think, written in the molecule. Yes, molecule and ion, not any particular atom. Okay, right. So total valence electron here, it is also, see in the phosphorus how many electrons in the valence shell? From electronic configuration all of you are knowing there are 5 plus oxygen. 6 valence electrons are there, so 6 into 4, 6 into 4, 3 negative charges there, so plus 3, so total 32 electrons, right? So in this way you can calculate the total valence electrons present in the molecule. Second point, I mean identify the central atom in the molecule. Identify the central atom, oblique ion in the molecule, right? Usually the less electronegative atom is the central atom. This is general rule. In general, less electronegative atom is the central atom. Central atom of molecule oblique ion. See, so the central atom is usually the, I mean, less electronegative atom, and generally it is less in number as well. In any molecule, the atom which is less in number, that can also you can find out the central atom. But where only 2 atoms are there, then how to decide which one is the central and which one the non-central? So this definition will help you to identify the central atom. Suppose that H2S is given. So H2S is given. H2O is given, NH3 is given. So now tell me which one is the central atom here. So these are the exception of this definition. This definition will work in most of the molecules, but here this will not work. So in this case, the central atom, in first case sulfur is the central atom, in the second case oxygen is the central atom, and in third case nitrogen is the central atom. But they are more electronegative here, and except these, in rest it is okay. So you can use the second definition what I have stated, that okay, the central atom is less in number. So here this is exception of this statement, general statement, right? So these are the exceptions. And similar exceptions you may have, more similar exceptions you may get. Suppose that now CCl4 if given, suppose that CCl4, so the central atom is C. Suppose that PO4 3- is given, so central atom is P, right? H2SO4 is given, so the central atom is sulfur, right? And suppose that IF7 is given, so the central atom is I, etc. Suppose that carbon dioxide is given, so the central atom is carbon. So this definition will help you in most of the cases, but few exceptions you may get. So if you use both the definitions, less number, right, or less electronegative. I mean both, if you use both the definition, both will solve your problem. Now the third point is write the central atom symbol and then arrange the other atoms around the central atom. So arrange the atoms around the central atom. Around the central atom. Right? Now the next point is fourth point. Distribute the electron in pairs. Distribute the electrons in pairs, right? So that is one pair, so that one pair of electron forms a single bond. Right? And then supply the electron pair. First, what you have to do, put one electron pair in all the atoms, between all the atoms, and now you can supply the electron pairs until each atom has an octet, right? So now supply electron pairs electron pairs, right? Until each atom has an octet, right? So in this way you can do. Don't see that how many electrons are there in the valence shell of central atom. You have to try to complete 8 electrons for each atom, and exception is hydrogen, right? Exception is hydrogen. So you have to along with this statement you have to use your skill also to find whether okay this is 8 electrons will there in the valence shell or only 2 electrons are there. So you have to all those previous concepts here, right? So first I am taking example ozone. See, there is no central atom, no secondary atom, all oxygen. So do step by step. Step 1, find the total number of electrons, valence electrons in this molecule. So total valence electron. So in the valence shell 6 electrons are there. So 6 into 3 is equal to 18 electrons, right? So total 18 electrons we have valence electron. How many electron pair? 9 electron pairs we have, right? So now you have to write what? Oxygen, right? In this manner you can write oxygen. Now what arrange the atoms around the central atom. I have arranged this one. I am considering central atom and other are okay, same atoms are there. Distribute the electron in pairs. So one electron pair is here, one electron pair is here. You have total 9 electron pairs. So remember, you have total 9 electron pairs, right? You have distributed 2 electron pairs. After that, what I have written? Now supply electron pairs until each atom has an octet. So see, I am supplying one more electron pair here, right? And make different permutation combination, but I am taking here this and here this. Now count the number of electrons here in this oxygen: 2 to 4 to 6 to 8. So oxygen complete. Now one electron pair here also I am distributed. So now see here, 2 to 2 to 4 to 6 to 8. This also has completed 8. Now how many electron pair you have distributed? See, 1 2 3 4 5 6 means 6 electron pairs you have distributed. You have total 9 electron pairs. Remember, 9 electron pairs. So you have left 3. So you can put 3 like this. Now you can put a bond. So O double bond O, O double bond O, and single bond O, and one lone pair here, 2 lone pair here, and 3 lone pair here, right? So this is the structure of what? Lewis structure of ozone molecule. In the simple manner you can distribute the electrons. So how many sigma, how many pi bonds are there? 2 sigma bonds are there, 1 pi bond is there, right? All have 8 electrons in the valence shell. So this is the, we can say this is one of the model of ozone molecule. I'm not telling that this model is perfectly okay, this is 100% okay, but this is very close to reality, right? So this is the way how to write the structure of Lewis structure of molecules, right? Okay, now do the practice on some more structures. For example, suppose that PO4 3 minus is given. Suppose that. Okay, so step 1, first you have to calculate total number of electrons. So total valence electrons is equal to phosphorus 5 plus 6 into 4 24 plus 3. So this is 32 electrons, means total 16 electron pairs. Total 16 electron pairs are there, right? Any doubt? No? Okay. Now see. What is the central atom here? Central atom is the phosphorus. So as the name itself indicated, so you have to write phosphorus in the center and write all 4 oxygens here like this. Okay, and now put electrons. First you have to put 1 electron pair between all the atoms, right, like this. And now how many? 1 2 3 4 4 electron pair you have distributed, and you have total 16 electron pairs.